Hello everyone, I am Shyama Sreekumar, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. Today, I will be giving a lecture on the topic pseudo-noise sequences, which is in continuation to the previous lecture on Introduction to Spread Spectrum Communication. This is a part of Module 5 in Digital Communication. The topics covered in this lecture are PN sequences, its properties and generation, generator polynomial, and gold codes. So you have already seen what is spread spectrum communication and what are its advantages. So it's mainly used to reduce the attack of a jammer by the use of a spreading code. So the two commonly used spreading codes are PN sequence and gold codes. Pseudo-noise sequences or PN sequence is a periodic binary sequence which will look like a noise waveform. It's generally generated using feedback shift registers. As you can see in this circuit, we are having M flip-flops which are connected serially and it is synchronized to a single clock signal. And we are having a feedback logic which takes the output of the M flip-flops and the output of the logic circuit is fed back to the first flip-flop. The final output sequence is obtained from the last flip-flop. So at the end of each clock cycle, the states of the flip-flop changes according to the logic circuit. Now, the PN sequence generated at the output depends on the initial state of the flip-flops, the feedback logic used, and the length of the PN sequence generated depends on the number of shift registers. If the feedback logic consists entirely of modulo 2 adders, then the shift register is said to be linear feedback shift register. In such a case, all zero state will not be permitted because if it enters into the zero state, then the shift registers continues to be in the zero state. Therefore, the period of the PN sequence which can be generated using LFSR can't exceed the value 2 raised to m minus 1. This minus 1 is to avoid the zero state. When the period is exactly 2 raised to m minus 1, it is called as maximal length sequence or M sequence. And the period of the maximal length sequence is given by n, which is equal to 2 raised to m minus 1. Now let's see an example for a maximal length sequence generator for m equal to 3. The feedback connections are chosen from the third flip-flop and the first flip-flop. So in the figure, it's clear that the input to the XOR gate is from S3 and S1. The output of the modulo 2 adder is fed back to the first flip-flop. The initial state of the flip-flops is assumed as 1, 0, 0. So as you observe in this table, you can see that the initial state is 1, 0, 0. After the first clock cycle, the output of S1 modulo 2 added with S3 is fed back to S0. That is 1 XOR 0 is 1 and it is fed back to S0. Now in this clock cycle, S1 will be shifted to S2, S2 will be shifted to S3 and the S3 will be obtained at the output. In the next clock cycle, again S1 modulo 2 added with S3, it is 1. It will be updated in S0. Then again S1 is shifted to S2, S2 is shifted to S3 and S3 is shifted to the output. In a similar manner, if we continue this operation, we will obtain the output sequence. But when you observe the output sequence, it is repeating after every 7th clock cycle. That is, the output of the PN sequence generated by LFSR repeats after every 2 raised to m minus 1 clock cycle, that is 7 clock cycles. The resultant maximal length sequence from the above example is obtained as shown in this figure. Here 0 is coded as -1 and 1 is coded as +1. As you can see, the length of the maximal length sequence is given by n equal to 2 raised to m minus 1. Here m equal to 3, so therefore the total length is equal to 7. As you can see here, the output repeats after 7 clock cycles. Now each bit or digit in this sequence is called as a chip. And the chip rate, that is the number of bits per second or chips per second, is denoted as RC chips per second. Therefore, the chip duration Tc is given as 1 by RC seconds. That is, it is the duration of one single bit. Now, a set of n continuous bits forms a PN sequence. Therefore, the total period of the maximal length sequence is given by Tb is equal to n into Tc seconds. Let's see an example. Here we are generating a PN sequence using a feedback shift register of length m equal to 4. The chip rate is 10 raised to 7 chips per second. Our aim is to compute the parameters PN sequence length, chip duration and PN sequence period. So the given parameters are m equal to 4 and RC equal to 10 raised to 7 chips per second. The PN sequence length can be calculated using the equation n equal to 2 raised to m minus 1, which is equal to 15. The chip duration Tc, it is a reciprocal of chip rate, so it is equal to 10 raised to minus 7 seconds, which is equal to 0.1 microseconds. The period of the PN sequence Tb, it is equal to n into Tc, which is equal to 1.5 microseconds. So in this example, we have determined the different parameters which is related to a PN sequence. Now let's see the properties of maximal length sequence. The first property is the balance property. It states that in each period of the maximal length sequence, the number of ones is always one more than the number of zeros. That is, the difference between the number of ones and zeros is always equal to 1. In the above example, the code word obtained was 001101. Here the number of shift registers m was equal to 3 and the length of output code word is n is equal to 7. When you observe the number of ones, it is equal to 4 and the number of zeros is equal to 3. So in general, the number of ones is equal to 2 raised to m minus 1 and number of zeros is equal to 2 raised to m minus 1 minus 1. Therefore, this code word satisfies the balance property. The second property of maximal length sequence is the run property. Run is a subsequence of identical symbols, ones or zeros within a period of the sequence. In this example, we have the sequence 001101. It can be divided into 4 subsequences. First subsequence is of length 2, second subsequence is of length 3 and it consists of ones, and third subsequence consists of a single 0 and the fourth subsequence consists of single 1. So it means that it has got 4 runs. Now run length property states that 1/2 the runs are of length 1, 1/4 are of length 2, 1/8 are of length 3 and so on. So, and also it's told that for a LFSR of length m, the total number of runs is n plus 1 by 2. So using that equation, we can see that here we are having 4 runs. Now when you try to prove the run property, when you consider length 1, 1/2 is of length 1. That is 1/2 of 4 is equal to 2. That means it consists of 2 subsequences of length 1. Now 1/4 are of length 2, that means only one run is of length 2, that is it contains 2 zeros. Now length 3, it is 1/8 of number of runs which is equal to 0.5, which can be approximated to 1, that means it consists of one run of length 3. Therefore, it satisfies the run length property. The third property of maximal length sequence is the correlation property. It states that the autocorrelation of a maximal length sequence is always periodic and binary value. That is, it will take only 2 values. It is having the maximum value of 2 raised to m minus 1 and a minimum value of minus 1. And 2 raised to m minus 1 is the sequence if it is not having any shift, that is tau equal to 0. That is, it is a correlation between the same copies of the signal, and it will be minus 1 for all other shifted versions. Now, when you see this example, it is 0, 0, 1, 1, 1, 0, 1. 0 is coded as minus 1 and 1 is coded as plus 1. Now, we are shifting the sequence from left to right. In the first shift, we take this minus 1 to the right side. So, the shifted version is obtained as this. Now, when you find the autocorrelation, that is, we are finding the product between the two sequences, and when we sum it up, we will get it as minus 1. In the next shift, we will shift this minus 1 to the right side. So, we will get the next one. Then, finding again the autocorrelation, we are again getting it as minus 1. When you repeat it, at the end of 7 shifts, we are obtaining back the same sequence. Now, when you multiply two same sequence, then we will get the maximum value which is equal to 7. That is 2 raised to m minus 1. The autocorrelation function of c of t in terms of integral is given by Rc of tau equal to 1 by tb integral minus tb by 2 to plus tb by 2 c of t minus tau dt. This autocorrelation function is a function of tau which represents the shift in the original Pn sequence. And Tb is the period of the waveform c of t, which is given by Tb is equal to n into Tc. When you try to plot the autocorrelation function as a function of tau, the maximum value will be obtained at tau equal to 0. And the maximum value is equal to 1. It is obtained when there is no shift in the Pn sequence. That is, the same sequence is correlated with each other. Now, after Tc seconds, that is after 1 bit shift in the Pn sequence, the autocorrelation function will reduce from a maximum value of 1 to a minimum value of minus 1 by n. Now, after n Tc seconds, that is after 1 period of the Pn sequence, the autocorrelation function goes back to the maximum value of 1. Therefore, when you observe the autocorrelation function, it is a periodic binary waveform with a maximum value of 1 and a minimum value of minus 1 by n. And the period is equal to n into Tc seconds. Now, in the previous example, we have seen that the autocorrelation function has a maximum value of 7 and a minimum value of minus 1. On normalizing these values, 7 by 7 is equal to 1. That is the maximum value, and the minimum value is minus 1 by 7. That is minus 1 by n. Now, when you take the Fourier transform of autocorrelation function, we will obtain the power spectral density. The power spectral density of this waveform follows the Singh square signal, and it consists of a number of impulse signals which are equally spaced at 1 by n into Tc hertz. So when you compare a maximal length sequence and a random binary wave, they have the similar autocorrelation function. Now when you observe the power spectral density, which is the Fourier transform of autocorrelation function, both have the same envelope which is proportional to Singh square ft. As you can see in this figure, this is the power spectral density corresponding to a random binary wave which follows the shape of Singh square function. Now the fundamental difference between the power spectral density of a random binary wave and a maximal length sequence is that both are proportional, or both have the envelope similar to a Singh square function, but for a random binary wave, the power spectral density is a continuous Singh function. But for an ML sequence, it consists of delta functions which are equally spaced at 1 by ntc. Now let's see an example in which we are trying to prove the properties of maximal length sequence. We are considering a PN sequence given as this, and we have to determine the number of shift register used as well as verify the balance property and run length property. Here the length of the PN sequence given is n equal to 31. Substituting in the equation n equal to 2 raised to m minus 1, we can get 31 is equal to 2 raised to m minus 1. On solving this equation, we'll get m equal to 5. Therefore, the number of shift registers used is 5. To verify the balance property, we'll find the number of zeros and number of ones. Number of zeros is equal to 15 and number of ones is equal to 16. Hence, the number of ones is always 1 more than number of zeros. Thus, the balance property is satisfied. Now, to prove the run length property, we will divide the given sequence into a number of runs, that is into subsequence of the same symbol. So when you divide it, we'll get the number of runs which is equal to n plus 1 by 2, which is equal to 16. That is, we are having total 16 runs. Now when you consider runs of length 1, it is 1/2 of the total number of runs. So 1/2 of 16 is 8, which means we are having 4 set of single zeros and 4 set of single ones. Now, number of runs of length 2 is 1/4 the total number of runs, which is equal to 4. So, we are having 2 sets of 2 zeros and 2 sets of 2 ones. Now, when you consider runs of length 3, it is 1/8, which is equal to 2. And when you observe this code, we are having 1 set of 3 zeros and 1 set of 3 ones. Now when continuing this procedure for length 4, it is 1/16, which is equal to 1. We are having 1 set of 4 zeros. For length 5, it is 1/32 of total number of runs, which is equal to 0.5, which is approximately 1, and we are having 1 set of 5 ones. Now when you add up all the runs, that is 8 plus 4 plus 2 plus 1 plus 1, we'll get it as 16. Hence, the run length property is satisfied. So, we have seen that in LFSR, we can generate a PN sequence by using a logic circuit. Now, what are the inputs to be fed to the modulo 2 adder determines the PN sequence generated. For that, we are using a special type of polynomial called as the primitive polynomial or the generator polynomial. A polynomial is said to be primitive if it can't be factorized, that is, it is in an irreducible form. And also, it is a factor of x raised to n plus 1, where n is equal to 2 raised to m minus 1 and m is the number of shift registers. So, as you can observe in this table, for a particular value of m, we will be having the tabs according to the primitive polynomial. For n equal to 2, the value of n will be equal to 3. So, a factor of x cube plus 1 will be chosen as the primitive polynomial. When you consider x cube plus 1, it is x plus 1 into x square plus x plus 1. So, the polynomial x square plus x plus 1 is chosen as the primitive polynomial. And the feedback tabs are determined by the powers of the polynomial. So, 2 and 1 are the positions where feedback is taken to the modulo 2 adder. Now, for m equal to 3, the value of n is 7. Now, factor of x raised to 7 plus 1 is given by x cube plus x plus 1. Now, the powers are 3 and 1. Therefore, the feedback tabs are 3, 1. Similarly, for each value of m, we have got a set of primitive polynomials. So, we can determine the tabs or the positions where feedback has to be taken according to the polynomial. So, for a value m equal to 5, we have got 3 different sets of polynomials. Similarly, for m equal to 6, we have got 3 different sets of polynomials. For each polynomial, the PN sequence generated will be different. So now let's compare the PN sequence generated for m equal to 5 using 2 sets of feedback connection. So here we have taken the feedback tabs to be 5, 2. So we have taken the feedback from the 5th flip-flop as well as from the 2nd flip-flop, and the output is fed back to the 1st flip-flop. Now, when you generate the sequence using the same logic, we have made the initial state of the shift register to be 1, 0, 0, 0, 0. Now, in each iteration or in each clock cycle, the output of second flip-flop XOR fifth flip-flop will be fed back to the first flip-flop, which is determined by the feedback symbol. And we have obtained the output symbol from the fifth flip-flop. So the output sequence thus generated is obtained as this, and it will have a length of 31, which is 2 raised to 5 minus 1. After 31 clock cycles, the same sequence will start to repeat. Now we are taking the same example of m equal to 5, but the feedback connections are 5, 4, 2, 1. So the output of the fifth is XORed with 4, then it is modulo 2 added with 2, then with 1 and fed back to the first flip-flop. So we are repeating the same procedure with the initial state at 1, 0, 0, 0, 0. Now we'll be determining the output symbol from the fifth flip-flop and we'll get the output sequence as this. And the output sequence will have the same length of 31 since we are using 5 shift registers. But it will be different from the previous PN sequence which was generated using the feedback tap connections 5, 2. Therefore, we can generate different PN sequence with the same number of shift registers by using different primitive polynomial. So, as the number of shift registers increases, we can have more number of primitive polynomials, hence more number of PN sequences can be generated. So, we have discussed pseudo noise sequence and its properties. So when you see the LFSR circuit to generate the pseudo noise sequence, we are having a feedback connection. Now, if the jammer can understand the feedback connection, then they will be able to trace back the information that is sent. Thus, if the jammer observes the PN sequence generated for a duration of 2m bits, then they will be able to understand the feedback connections. It is due to the linearity property of the PN sequence generator. But if the bits are combined in a non-linear manner, then it will become more difficult for the jammer to understand it. And also, when you observe the cross-correlation properties between any two element sequence, it will be having relatively large values. These are actually the drawbacks of our conventional PN sequence. So, this table shows the comparison of P cross correlation for different values of M. As you can see from this table, we have got M varying from 3 to 12, and when you observe the P cross correlation, it is varying from 5 to 1407. That is, the cross correlation is fairly high as the length of the shift register increases. So using PN sequence, the cross correlation is having a relatively high value. So when you consider CDMA systems, that is code division multiple access system, the different users are allocated codes which is having little cross correlation. So such PN sequences are undesirable, that is the ML sequences are undesirable in such cases. So we go for PN sequences which much better cross correlation and it is called as gold codes. So when you observe the correlation property of PN sequence, we told that it is having a relatively large value. Here we are taking the example of m equal to 7. So we can have PN sequences of length 127. Now we are using 7. We consider two primitive polynomial, one with connection 7, 4 and one with connection 7, 6, 5, 4. So here when we plot the autocorrelation function, it is having the maximum value at tau equal to 0 and the magnitude is equal to 127, and all other points the autocorrelation will be minimum. Now if we obtain the cross correlation between the two sequences, then it will be varying between a large range of value. and the maximum value is obtained is 40. So when you observe the cross correlation of PN sequence, it is relatively poor. Therefore, to get better cross correlation property than PN sequence, we go for gold codes. So according to Gold's theorem, we are having two primitive polynomials g1 of x and g2 of x, which is of degree n. And each maximal length sequence will be of period 2 raised to n minus 1. According to Gold, the cross correlation will be having a magnitude which is less than or equal to 2 raised to n plus 1 by 2 plus 1 for odd values of n, and 2 raised to n plus 2 by 2 plus 1 for even values of n. For such cases, we are using the product polynomial, that is g1 of x and g2 of x, for generating gold codes, and it can generate 2 raised to n plus 1 different sequences using sequences of period 2 raised to n minus 1. So when you consider gold codes, we are generating the gold code using the modulo 2 addition of the two separate PN sequences. That is a PN sequence generated by 7, 4 and a PN sequence generated by 7, 6, 5, 4. And the resultant PN sequence which is obtained is called as the gold codes. Now here you are having two separate sequence, 1, sequence 2, each will be having a period of 127. Now we have already stated the Gold's theorem. In that we are told the correlation function will have a magnitude less than or equal to 2 raised to n plus 1 by 2 plus 1 if n is odd. So the value of cross correlation will be less than or equal to 17. So here we are seeing that we are forming a gold code using the modulo 2 addition of two different LFSRs 7, 4 and 7, 6, 5, 4. Now the cross correlation function between the different gold code is as shown in this figure. Now the maximal value of the cross correlation is limited to 17. As stated in Gold's theorem, there can be 2 raised to n plus 1, that is 129 sequences that will satisfy the condition of cross correlation. Therefore, when you compare maximal length sequence and gold codes, the gold code is having much better cross correlation properties, and the maximal value is also less when we compare it with maximal length sequence. So therefore, in this lecture, we have studied PN sequences, its properties, generation, its drawbacks, and then we have also seen the properties of gold codes and how to generate gold codes. Thank you.